We often take for granted the humble thread, yet this simple helix is what holds our world together. These spiraled structures are more than just a means to fasten objects. They are the backbone of countless engineering feats. From the largest bridges that span rivers and valleys to the smallest gadgets that fit in the palm of your hand, threads and fasteners are the unsung heroes of engineering. They provide the strength and stability needed to keep everything in place, ensuring that our creations stand the test of time. But have you ever stopped to think about how these crucial components are represented in the technical drawings that guide their creation? These drawings are the blueprints that engineers and manufacturers rely on to bring their designs to life. Accurate thread representation is paramount in the world of engineering. Without precise depictions, the integrity of the entire project can be compromised. Every line, every symbol, and every detail must be meticulously crafted to ensure that the final product functions as intended. A single misplaced line or an inaccurate symbol on a technical drawing can spell disaster, leading to manufacturing errors, assembly mishaps, and ultimately compromised functionality. Imagine the chaos that could ensue if a critical component fails because of a tiny mistake on a drawing. That's why understanding how to properly depict threads in mechanical drawings is essential for anyone involved in the design, manufacturing, or inspection of mechanical components. This knowledge ensures that every part fits together perfectly, maintaining the integrity and safety of the entire structure. So, let's dive into the world of threads and explore the art of accurately representing these tiny but mighty elements. By mastering this skill, we can continue to build and innovate, creating engineering marvels that stand the test of time. Whether you're an experienced engineer or just starting out, understanding the importance of threads and their representation in technical drawings is a crucial step in your journey. Imagine a world where blueprints were vague, where a line representing a thread could be interpreted in a multitude of ways. Chaos would reign in the manufacturing plants. Accurate thread representation provides a universal language that everyone involved in the manufacturing process can understand. It eliminates ambiguity and ensures that everyone is on the same page, literally. For manufacturers, precise drawings translate to parts that fit together seamlessly. Assembly becomes a breeze, saving time, money, and frustration. Inspectors rely on accurate drawings to verify that threads meet the required specifications, ensuring quality control and product integrity. Think of it this way. Proper thread representation is the difference between a well-oiled machine and a pile of ill-fitting parts. Now that we understand the importance of accurate thread representation, let's explore the different ways to depict threads in technical drawings. Just like there are different levels of detail in a photograph, there are different levels of detail when representing threads. The most detailed method involves drawing the exact helical profile of the thread. This approach provides the most information but can be time-consuming, and is typically reserved for situations where extreme precision is required. A more common approach is the schematic representation, where the major and minor diameters of the thread are represented by concentric circles. This method strikes a balance between detail and efficiency. Finally, the simplest representation shows only the major diameter of the thread. This method is often used for simplified diagrams or when space is limited. And Section 4, Drawing External Threads, a step-by-step guide. In this section, we will delve into the intricate process of creating external threads, which are essential components in many mechanical assemblies. These threads are commonly found on bolts, screws, and studs, and they play a crucial role in fastening and securing parts together. Let's start by dissecting the art of drawing external threads, those found on bolts, screws, and studs. Picture a standard bolt. This bolt is a fundamental element in mechanical engineering, and understanding how to accurately represent its threads is vital for any technical drawing. The part you grip with a wrench is the unthreaded shank. This section is crucial as it provides the necessary leverage for tightening or loosening the bolt. The shank is typically smooth and cylindrical, allowing for easy handling and manipulation. The threaded portion where the nut engages requires a specific approach. This is where the magic happens, as the threads interlock with the nut, creating a secure and reliable connection. Properly drawing this section is essential for ensuring the functionality and strength of the bolt. First, draw the shank diameter using a thick, solid line. This line represents the outermost boundary of the bolt's shank and sets the stage for the rest of the drawing. It's important to get this right, as it forms the foundation for the entire thread structure. This represents the major diameter of the thread. The major diameter is the largest diameter of the thread and is a critical dimension in ensuring that the bolt fits properly with the corresponding nut. Next, draw a thinner line parallel to the shank, representing the minor diameter. The minor diameter is the smallest diameter of the thread and is equally important in defining the thread's profile. This line helps to create the depth and shape of the threads. Now for the telltale signs of a thread: short, angled lines, almost like tiny teeth, drawn perpendicular to the center line of the thread. These lines are crucial in depicting the helical structure of the threads, which allows them to engage with the nut effectively. These represent the crests and roots of the thread. The crests are the peaks of the threads, while the roots are the valleys. Both are essential in defining the thread's geometry and ensuring a proper fit with the nut. Don't forget the chamfer. At the end of the threaded portion, add a small angled line to represent the chamfer, which helps to start the nut. The chamfer is a slight bevel at the end of the threads, making it easier to engage the nut and start the threading process smoothly. This small detail can make a big difference in the ease of assembly and the overall performance of the bolt. Section 5. Drawing internal threads, navigating the ins and outs. Internal threads found in nuts and tapped holes require a slightly different approach. Imagine looking down into a nut. You'd see the threads spiraling inwards. Begin by drawing the hole diameter using a thick, solid line. This represents the minor diameter of the thread. Next, draw a thinner, dashed line slightly larger than the hole diameter. This represents the major diameter of the thread. The short, angled lines representing the thread crests and roots are drawn in the same way as for external threads, but they are positioned differently. For internal threads, these lines are drawn on the inside of the major diameter circle, and of course, don't forget the chamfer at the entrance of the hole. Section 6. Speaking the language of threads, symbols and callouts. Just like any other feature on a mechanical drawing, threads have their own set of symbols and callouts that convey essential information about their size, pitch and type. These symbols and callouts are crucial for ensuring that the threads are manufactured and assembled correctly. Without these precise notations, it would be nearly impossible to achieve the desired fit and function of the threaded components. Think of these as the thread's ID card. Just as an ID card provides vital information about a person, thread callouts provide all the necessary details about the thread. This includes the thread's dimensions, the type of thread, and other specific characteristics that are essential for its application. For metric threads, the letter M, followed by the major diameter and pitch, is used. This system is standardized and widely recognized, making it easy for engineers and machinists around the world to understand and implement. For example, M10 by 1.5 represents a metric thread with a major diameter of 10 millimeters and a pitch of 1.5 millimeters. This notation is clear and concise, providing all the necessary information at a glance. Unified threads, commonly used in the United States, are designated by the inch symbol followed by the number of threads per inch in the thread series. This system is different from the metric system, but serves the same purpose of providing detailed information about the thread. For example, 1/4-20 UNC represents a unified national coarse thread with a diameter of 1/4 inch and 20 threads per inch. This notation helps in identifying the thread type and its specific characteristics, ensuring that the correct thread is used for the application. These callouts are typically placed near the thread representation, connected by a leader line. The leader line acts as a pointer, directing the viewer's attention to the specific thread being described. This helps in avoiding any confusion and ensures that the correct thread specifications are followed during the manufacturing process. Understanding these symbols and callouts is essential for anyone involved in the design, manufacturing or assembly of threaded components. It ensures that the threads are produced accurately and function as intended, contributing to the overall quality and reliability of the mechanical system. Section 7. Fasteners at a glance. Standard symbols and shapes for bolts, nuts and more. While meticulously drawing each individual thread is important for detailed representations, there are standardized symbols for common fasteners like bolts, nuts, washers and screws. These symbols simplify the drawing process and make it easier to interpret technical drawings at a glance. For example, a bolt is typically represented by a rectangle with a thick line representing the shank and a thinner line representing the thread. A nut is represented by a hexagon, and a washer is represented by a simple circle. These symbols are often used in conjunction with simplified thread representations, where only the major diameter of the thread is shown for clarity.